Okay, welcome to the week 8 of the problem solving session for the Introduction to Fluid Mechanics course, whose course is instructed by Professor Suman Chakraborty. So, myself Kalpita Nath and just one second. And I am research scholar at IIT Kharagpur. So, with this introduction, we'll start with today's session. Okay, let us wait for 5 minutes for others to join, and then we'll proceed with today's session. I hope I am properly visible and audible. Okay, so let's wait for 5 minutes then. Okay, I think we should start with today's session. So let me share the writing pad. Okay, so I hope the writing pad is visible. First of all, we'll go through what sir have taught in the class. So this whole week was based on like the derivation of, like, sir gave different examples of how to use the Bernoulli equation. So with that thing, and even different devices, he also talked about different devices like venturimeter where the Bernoulli's equation can be applied, or different phenomena, right, where like a tank is there, water is flowing from one point, like let's say at the bottom or at the sides. So how to measure the velocity or the pressure gradient, like that. So with that brief, let's go through what sir have taught, like few of the examples. So first thing that he started with was, like, if so we know that the streamline coordinate of the streamline is different as compared to the xy coordinate. So first of all, if this is the streamline coordinate, like this is x and this is n. Okay, so this is r. There's a radius of curvature of the streamline. This is the streamline. Let's suppose this is the point xy. Okay. So at the point xy of the streamline, the velocity vector is given, let's suppose v vector is given as ax square I cap minus 2axy j cap. And we want to find out what is the radius of curvature r, this radius of curvature of the streamline at point x and y. Now, first and foremost, for this kind of problem, every of this kind of problem, we need to first check whether the flow is compressible or not. So let's go for that. So for checking the compressibility, we will check del u del x. So del u del x is 2ax, and del v del y. Sorry, del v del y, that is minus 2ax. That means del u del x plus del v del y is equal to 0. That means the flow is incompressible. Let us now first find the acceleration at point 1, sorry, xy. So acceleration can be given as axi cap plus ay j cap. So we want to convert this x and y coordinate to the coordinate of the streamline system. So streamline coordinate system has a unit vector in s direction here and unit vector in n direction. Okay, so n direction. So the acceleration will be as as epsilon s cap plus, we just need to convert this because we need to find the equation along the streamline. We can't find anywhere else, right? So in the previous day we did some derivation, right? So where we found this an. So an we know as minus v square by r, where v is equal to root over u square plus v square. Those are the components of velocity.
Now we need to find r from here. So this r we need to calculate. So first let us find out the unit vectors, this epsilon s cap and epsilon n cap. So the unit vectors along s and n direction. So first of all, we know that ax equal to u del u del x plus b del u del y is equal to ax square to ax plus minus 2axy multiplied by 0. And this will give us what? This will give us a 2a square x cube. 2a square x cube, right? Now, we also find ay. Ay will be u del v del y, sorry, x plus v del v del y, right? Now, this will give us ax square minus 2ay plus minus 2axy minus 2ax. So this is equal to minus 2a square x square y plus 4a square x square y. That is equal to 2a square x square y. Now, v is oriented along s, right? That means v, the velocity vector, is oriented along this s coordinate of the streamline. So we can write epsilon s cap as v vector. The unit vector along v will be the unit vector along s. So along the streamline. So this is the unit vector of velocity. Now we need to find epsilon n cap. So how can we find that? So if we want to find that, let's suppose, let us take that this is the plane and this is s, this is n. So let us take another color. This is x and this is y. This is the resultant of x and y, right? This is a vector, that is the resultant acceleration. This is epsilon s cap, this is epsilon n cap. This is z and k cap. Now, if we will do this, we can clearly see from here, na, that this k cap and s cap, if we will cross, then we'll find this n cap, right? So with that context, let's do it. So let's suppose s is equal to x and n is equal to y. Oh no, sorry, 1 second. Now if we will do cross product, k cap cross epsilon s is equal to epsilon n. So this we know, this we know, this we can find out. Now a n vector we need to find out, that will be a vector dot epsilon n cap, right? And we need to equate with minus v square by r, that is the value of a n cap, a n vector. Now we need to find this one at last, right? So for this one we need to first find epsilon n cap, and for epsilon n cap we need to first find what was epsilon n cap. Epsilon n cap is, just see, sorry, epsilon s cap. Epsilon s cap is this one, right? Epsilon s cap is v vector unit vector, the unit vector of v vector. So v vector, first we need to find out, that will be v vector mod, that means the amplitude of or the value of v vector, that is ax square plus minus 2axy whole square. That will give us root over a square x to the power 4 plus 4a square x square y square. Actually, sir, I have not solved in the class, so I am solving it by myself. If there is any problem, you can point me out. Okay. So epsilon s cap will be v vector upon v vector. That will give the magnitude of that. So this will be x a x square I cap minus 2 a x y j cap upon root over a square x to the power 4 plus 4 a square x square y square. So this will be a x square I cap minus 2 a x y j cap upon a x root over x square plus y square. So epsilon s cap will be is equal to x upon root over x square plus 4y square I cap minus 2y upon root over x square plus 4y square j cap. So we need to find epsilon n cap now. So epsilon n cap is equal to k cap cross epsilon s cap. So that will give us I, j, k, 0, 0. K means only on z direction, right? And that will be 1. So, and epsilon s we have already found out root over x square plus 4y square. I may be wrong somewhere. Please point me out. So this is x square plus 4y square. This is 0. So this is equal to I cap 2y by root over x square plus y square 4y square minus j cap minus x by root over x square plus 4y square. So this is equal to epsilon n cap. So we already found that out, right? So this will be 2y by root over x square plus 4y square I cap plus x upon root over x square plus 4y square j cap. Now a n vector is equal to a n I cap, sorry, a x I cap plus a y j cap. So a n will be the acceleration dot product of acceleration and epsilon n cap, where we have written that earlier, right? Just 1 second. We've already derived that earlier. Yeah, this one and this one. So we need to find just a n cap. So just a n cap, a n cap. So sorry, a n vector. Sorry, a n vector. So if you find a n vector, that will be a vector dot epsilon n cap. So simply we are doing that. So this will be here. So if you will multiply that and that a n cap will be is equal to minus v square by r. So this is equal to 2y a x upon root over x square plus 4y square plus x a y upon root over x square plus 4y square. This will be equal to minus v square by r. This will be equal to minus root over ax square whole square plus minus 2axy whole square. This will be r upon r. So this is like, if we will find that out, that will be 2y upon root over x square plus 4y square multiplied by 2a square x cube plus x upon root over x square plus 4y square and multiplied by 2a square x square y. So this will be is equal to minus root over a square x to the power 4 plus 4a square x square y square upon r. So that will be is equal to minus ax root over x square plus 4y square upon r. Or this will be 4y ax square plus 2ax square y is equal to minus x square plus 4y square by r. or r is equal to minus x square plus 4y square upon 6x square ay. So this is the radius of curvature for the given problem. Okay, you get an understanding of this. We'll take a break of 1 minute or 2 minutes rather. Okay, should we proceed forward? I think let's proceed to the next example that sir have discussed about. Okay, so if sir told about bent in an horizontal duct, that is example 2. So if there is a bent in the horizontal duct like this, okay, my drawing is very bad, pardon me for that. It will be like this. So if we draw a streamline over there, this will be somewhat like this, parallel streamlines. Okay, so let's suppose we take a radius r and dr thickness of an element there. This is r2, this is r1. This is this part of a circle. Let's suppose this is an arc and part of a circle. Now, circular curves have radius of curvature constant. Thus, if we use polar coordinate system, that means r theta, that is equivalent using to SN coordinate system. Then r is always oriented in n direction. R is always oriented in n direction. Okay. So the width of the okay. So first what we need to do, what is given to us? Given that v theta is equal to c by r and vr is equal to 0. That means this flow is flow of free vortex. Free vortex flow are those flows that has only v theta component and no vr component, and v theta is a function of r. Now let's say that the mass flow rate is given as m dot. and steady flow, the flow is given as steady flow, inviscid flow, and density is constant. A free vortex flow is irrotational, and an irrotational flow remains irrotational for inviscid flow, right? So now what is the objective? Objective is we need to find P2 minus P1. There is a pressure difference between points 1 and 2. Now for SN coordinate, we have already derived earlier that del P del N is equal to rho V square by R, right? We have already derived that earlier. If streamlines are parallel, we can use that. Now N vector is equal to R vector, that is known, we have already discussed about it. So this can be written as this V, this means this V theta, that is only on one velocity component. So as V is a function of theta only. So this can be written as rho C square by R cube. Now if we integrate it, if we integrate it, one second. If we integrate it, that means P2 minus P1 is equal to rho C square rho C square R1 to R2 R to the power minus 3 dr. That means this will be rho C square by 2 R2 square upon minus R1 square upon R2 square R1 square. But we do not know C, as V theta is a function of 1 upon R and C is just a constant. So to find C, we need the description of m dot as m dot is given. So how do we need to find m dot? Now if we go back over here in this diagram, the width of the duct, like as we have already selected a small region over here, the width of that duct perpendicular to the plane of figure, like first of all it's given that the width of the duct perpendicular to the plane of figure is B, width is B, and the area of this strip then will be BDR, right? Now the volumetric flow rate flowing through that strip is V theta is perpendicular to that area. So V theta multiplied by BDR. Now the mass flow rate will be multiplied by density, right? So m dot will be is equal to R1 to R2 V theta rho BDR. That means V theta is equal to C by R. So C by R, V theta is C by R. So when we'll integrate it, it will be rho BC ln R2 upon R1. This is m dot, and m dot is given, right? So now m dot is already we found out. So C from there, if we find C from there, that will be m dot upon rho B ln R2 upon R1. That means if we write in the main equation, P2 minus P1 is equal to rho m dot square upon 4 rho square B square ln R2 upon R1. R2 square minus R1 square upon R2 square R1 square. This m dot can be measured, like this mass flow rate can be measured by an instrument. There are many instruments where we can measure, and if this all of these are known, then P2 P1 can easily be calculated. Now another point is the use of Bernoulli equation, like this this is method 1, right? Now another method that we can apply is use of Bernoulli equation. That is very easy process. Now Bernoulli equation can be applied between points 1 and 2, right? Let me first introduce you the points. So this is point 1 here at the inner circle, and this is point 2 at the outer circle, but they are not located on the same straight line, right? But if we still apply that, then P1 by rho plus V1 square by 2 is equal to P2 by rho plus V2 square by 2. We're considering they're on the same horizontal line, so P2 like on the flat on the paper direction. So P2 minus P1 is equal to rho by 2 V1 square minus V2 square. So this is equal to V theta with just one second, v theta 1 square minus v theta 2 square. So this is equal to c square 1 upon r1 square minus 1 upon r2 square. So this is equal to rho c square by 2 r2 square minus r1 square by r2 square r1 square. Now the result is same, right, as we have seen earlier, but these are not on the same streamline. So how come the result is same? How? So as the flow is irrotational, we can use Bernoulli equation among any 2 points, whether or not they are on the same streamline. If the flow is not irrotational, then make sure that point 1 and 2 are lies on the same straight line. For irrotational flow only, we like streams, the points should not may not lie on the same streamline. Still, Bernoulli's equation is valid, right? That's why you got the same answer. Now, another thing that we will talk about now is unsteady Bernoulli equation. I'll give you time for 2 minutes to gather what I have already taught, and then we'll proceed with this further. Okay. So not always the Bernoulli equation will be steady, like, and the conditions will be steady as well. So if we like take a big, huge tank, and there is a hole at the bottom, right? It's a small hole. There is a free surface, And here if we draw the streamline, it will go like this, right? Now let's suppose this is the main line and this is height h, this is diameter d, this is small dia d, right? At t is equal to 0, h is equal to h naught, and flow is unsteady. Obviously, the height is changing with time, right? Now, let us consider that the flow is inviscid and the density is constant. Let us consider this is, let us consider this is point 1, and here if we'll take here, this will be point 2. Now, what do we need to find out here? For unsteady state Bernoulli equation, this let us write the equation P1 by rho V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2 plus 1 to 2 dV del V del T ds. Now this is the extra term that is there for unsteady state Bernoulli equation. Now the both of them are at atmospheric pressure, so P1 and P2 cancels out. Now Z1 minus Z2 will be is equal to HT. That is also a function of T. Time increases, side decreases. Now A1 V1 is equal to A2 V2. Now V1 D1 square is equal to V2 D square. So V1 is equal to minus dH dt. So how do you express dVdt, del V del T in terms of like in terms of constant, that thing that we already know, but we do not know how that V varies with time, right? This V varies, how V varies with time, we do not know. If as compared to other terms, this is not important, we can simply drop that. If not, we have to assume it's with something. So let's suppose if dV dt is equal to constant. So if dV dt is equal to constant, 1 to integration 1 to 2 del V del T ds will be is equal to del V del T S2 minus S1. So S2 S2 minus S1, if we consider a streamline in between 2 and 1, like here, then this will be nearly S2 minus S1 will be is equal to nearly is equal to H. If we consider a streamline along the axis passing through 1 and 2, then, but this del V del T cannot be constant, right? So let us consider del V del T is equal to del V1 del T. Except from very close to the outlet, the streamlines are always parallel to each other almost. This may represent that the case where V is not varying with time, but very much like we consider a stream tube where the streamline forms an envelope, like this will be like a stream tube, like here all the streamlines are there, but point 2 is very small in comparison to the time. Thus we can even imagine that del V del T is equal to del V1 del T. That is wrong, but that give an approximate idea of what is happening. So we can even write 1 to 2 del V del T ds will be is equal to dV1 dTh. Now the main equation is V2 square minus V1 square upon 2 is minus G Z1 minus Z2 is equal to minus dV1 dTh. This is equal to H. And let's suppose this is term A and this is term B. And H is a function of T. Right. Now, let's compare the terms A and B. Like if we compare terms A and B, dV1 dTh upon GH, if it is far less than 1, that means B is far less than A, then we can neglect B. If B is comparable to A, then we need to keep this in differential equation form and cannot be that, but that cannot be solved analytically. Now A1 V1 is equal to A2 V2 according to continuity equation, right? So can also be used when the flow is unsteady. Acha. Now continuation A1 V1 we can A to V2 we can use here even if the flow is unsteady. Why? As this was derived initially from the equation continuity equation where del rho del T is equal to 0. That means density is constant. The flow may still be unsteady as the velocity may be a function of time, but density not being a function of time, a1 v1 is equal to a to v2 can be applied. So this is valid. This is valid for unsteady flow where density is constant. Okay. Now let us give you another example. Example 3, and you try and solve this. Like there is a plate here, and this is above a static fixed surface, and this is the axis of rotation. There is some distance r. If we calculate the velocity profile here, velocity profile, we consider it inviscid flow. So velocity profile is uniform, though it changes with radius, but it like this is the radius, right? This is total r. If this is the radius, this is circular plate. If this is the radius, and this plate is actually moving this side with a velocity v, and the fluid is squeezing out on the sides. So if I draw a streamline over here, it will be somewhat like this. It will be somewhat like this, right? Somewhat like this. Now, as the plate comes down, water is squeezed out radially outward, and thus, if this is B, B decreases. B decreases as time increases. Now we need to find, so let's suppose B is equal to B naught at T is equal to 0. We need to find out pressure as a function of R. Density, let's suppose density is constant and viscid flow. The rate at which the plate is coming down will be is equal to the rate at which fluid is squeezed out. So if we apply continuity equation A1 V1 is equal to A2 V2. Now consider a local radius R. So A1 is equal to pi R square. V1 is equal to V. V is not a function of T, and V is equal to constant. The rate at which the plate comes down. Now A2 is equal to 2 pi RB. If I take this small element, right? We are taking this small element. So A2 is equal to 2 pi RB, and V2 is equal to V2R is VR. Now A1 V1 is equal to A2 V2, and pi r square V is equal to 2 pi RB VR, and VR will be is equal to V into R by 2B. Now unsteady flow, if we need to retain the unsteady term in Bernoulli equation, P1 upon like if we apply Bernoulli equation now, P1 upon rho plus V1 square upon 2 plus GZ1 is equal to P2 upon rho plus V2 square upon 2 plus GZ2 plus 1 to 2 D del V del T Ts. This is applied between points 1 and 2 at small r is equal to small r is small 1. Sorry, point 1, and small r is equal to capital R is 0.2. So GZ1 is equal to GZ2, and P2 is the atmospheric pressure. P2 is the atmospheric pressure. So P2 is the atmospheric pressure is equal to PA, and V2 will be is equal to, like, let me write this down, then it will be easier for you to understand. So GZ1 is equal to GZ2. So P2 is equal to P atmosphere is equal to PA, and V2 is equal to VR is equal to V into R by 2B, V1 is equal to V. Now if we put everything down, P1 minus PA rho V square by 8B square, capital R square minus small r square plus 1 to 2 del V del T ds. Del V del T is equal to del V del T is equal to del VR by del T, and VR is VR by 2B, B is a function of T. This del V del T is equal to del VR del T, and B is a function of T. Del VR, sorry, VR is equal to and that VR is equal to VR upon 2B. Right. Now, we can write that minus dB dt is equal to B, and del V del T is equal to VR by 2B square multiplied by V is equal to V square R by 2B square. And ds can be written as dr if we choose the streamline is such a way that ds is equal to dr. So p1 minus pa upon rho is equal to v square by 8b square r square minus r square. So plus small r to capital R, v square r by 2b square dr. So v square by 4b square, this will be is equal to v square by 4b square r square minus small r square. uh, p varies with time as b varies with time, p varies with time as v varies with time, sorry, b varies with time, so that at given instant we have to find a value of b, so that a value of p can be calculated. How to find b at a given time? Minus, now minus db dt is equal to v. So from here you can write b is equal to b naught minus vt, can be found out at a given instant. Now substitute this in the main equation of this. So if this will be done, then we can find out P1, right? It's very easy. Okay. So we'll now go for some applications of Bernoulli equation. Let us take a break of 2 minutes. Okay, so let's proceed with some examples or applications of Bernoulli equation now. So first of all, we'll learn about what is siphon. So if there is a huge tank and let's suppose there is a free surface, we place a pipe there and we collect the water up to here, right? And this height is h from the free surface. Let's suppose this is point 1 and let's suppose this is point 1, point J, and this is point 1, this is point 2. Now let us consider, if we consider a streamline in between those 2 points, like this is a streamline between these 2 points. What can maximum height h max up to which the fluid in the tank can traverse vertically? What is that maximum height? If we consider streamline and we apply Bernoulli equation in between those 2 streamline, then P1 upon rho plus V1 square upon 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. Now, V1 as tank is very large, so V1 can be considered as 0. P1 and P2 are both at atmospheric pressure. No, not P2, sorry. P1 is at atmospheric pressure and V2 is same as the fluid that is ejected here, that is Vj. V2 is equal to Vj. So, Vj is equal to root over 2gh. This can be easily found out if you apply Bernoulli equation between point J and point 1. Right? Now, if we will apply like here P2 upon rho is equal to, if we are applying gauge pressure, so we are taking gauge pressure, so P atmosphere can be taken as 0. So, G H minus Vj square by 2 and this Z cos Z1 minus Z2 is equal to H, right, minus H rather. So that means the pressure at point 2 is below the atmospheric pressure. If the pressure at point 2 is negative, right, so that means it is, because it is negative and below the atmospheric pressure, P2 is below vaporization pressure, sorry, vapor pressure at that local temperature. But there is one concept called cavitation. What you know what happens as it is less than vapor pressure, air bubbles form that gets entered into the liquid, and that will shoot on that pipe and will destroy the siphon. In order to avoid that, we have to keep such a height that the pressure does not go below the vapor pressure, right? So that will give us maximum height. Now another example is like he told about he told about the static tube and the stagnation tube, right? Like if there is a pipe, like mm, there is a tube over here and fluid, if I apply attach a tube, fluid will rise here. So this is the central line, this is point A, this is point B. If we apply a tube over here and a horizontal pipe and we are making holes on that, and the height up to which the fluid rises will give an idea of the local pressure at that point, right? But if we if we consider the streamlines are parallel, then the pressure at the center line, that is A, will be equal to at point B, right? Now let's suppose we want velocity. So we want velocity, so if we like apply another pipe over here like that will be moving to the center line. So what will happen? The fluid will come to rest immediately at this point. Like if let us consider this point 2 and this point 1 now. So the flow will come to dead stop. So it will enter the tube and will rise in this tube. So obviously this pressure will be more. How? Because here the local pressure and also the kinetic energy, as it is come to stop, the velocity is 0, the kinetic energy, both of that will give rise to the height of the fluid. Now, what is static pressure? Pressure which is there because of the intermolecular collisions. So the pressure just felt the pressure that is just felt by moving with the flow is static pressure. Now, what is stagnation pressure? Pressure that is present at the point if the fluid is subjected to zero velocity. That is means at rest. At that point is a reversible. Sorry, if the process is reversible and adiabatic. If we apply the Bernoulli equation at point 1 and 2, that means P1 by rho plus V1 square by 2 plus, sorry, is equal to P2, like it is horizontal, so Z1, Z2 won't be there, so it will be equal V2 square by 2. So V2 will be is equal to 0 as there is stagnation point, so P2 is equal to P1 plus half rho V1 square. So this is static pressure, this is stagnation pressure. This is derived considering a frictionless condition. Pressure at point 2 will be stagnation pressure only when the fluid is brought to rest by reversible adiabatic manner. Stagnation pressure is not always required to find out, as we can simply find that out using a static pressure. Using static pressure plus half rho V2 square, sorry V1 square. Now another thing that sir have taught you is the venturimeter. Like if the pipe is there, like this pipe is there, and we apply another device that is called venturimeter in between, like it will be a decreasing, then a throat portion, then diverging part. This is converging section, this is throat, this is diverging section or diffuser. Now let's suppose this is the center line, this is point 1 and we apply a manometer here, like manometer is like that, this is point 2, right? So this is the fluid up to point here. This is like let's suppose this is Z1 and this distance, like this distance is Z, this distance up to point here, if we'll extend this here, this is Z2 and this is del H. This is density of the mercury. Bernoulli equation, if we are applying between point 1 and 2, then P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. Pressure at point A and B are equal. Pressure at point A and B are equal. Which one is point A and B? This is point A and this is point B. So if that is equal, then pressure at point A means what? P1 plus rho GZ1 and at 2 means P2 plus rho G Z2 minus del H plus density G del H. So, if we write this together, P1 plus rho G Z1 minus P2 plus rho G Z2 is equal to rho M minus rho G del H. So, that means rho G del H. So, that means del H is positive and this is also positive. That means this is positive. That means if we will write this, we can write this as like this thing, that is P upon, if we write in the form of head, P1 upon rho G plus Z1 minus P2 upon rho G plus Z2 is equal to rho M upon rho minus 1 into delta H. So this is piezometric head, right? The manometer measures doesn't measure the normal difference between 2 points. It measures the piezometric pressure difference, right? Pressure difference between point 1 and 2. If you write in terms of volumetric flow rate, Q is equal to A1, B1 is equal to A2, B2. So B1 is equal to Q upon A1 and B2 is equal to Q upon A2. So this we can write like, oh, obviously this will be also equal to V2 square minus V1 square upon 2G. So this can be written as, Q square upon 2G 1 upon A2 square minus 1 upon A1 square. So this is rho m upon rho minus 1 delta H, right? So this Q we can find out from here. This is it for today. Rest you have already taken the classes, so I think we should proceed with today's session. Like the explanation part is over. Now the question part. So this is the first question for today. A student successfully siphons water over a 8.5-meter high wall at sea level, and she then climbs to a mountain that is at an elevation of 4390 meter, and atmospheric pressure at that point is 58.5 kilopascal, and attempts the same experiment. Will she be successful? Neglect the fictional effects in the tube and cavitation. So what will be the option? I'll give you 2 minutes. You just think about it and then answer me. Okay. So here we know that the atmospheric pressure is what? Atmospheric pressure is 101.3 to 5 kilopascal, right? At sea level. So when she climbs to the mountain, that pressure was 58.5 kilopascal. So obviously that is less as compared to the sea level. So if let's suppose this is the free surface and this rises like this is a siphon and this rises up to a height like at point 2. So if this is point 1, if this is point 1 and that is point 2, this height is greater than 8.5 meter. It's already said. At this point, now if this is point 2, at this point the maximum height is reached and thus the velocity will be 0. So if we will apply like the Bernoulli's equation, like let's suppose we can get the height. So this is P atmospheric pressure plus rho g h for this height h. For this height, let's suppose this height is h. So rho g h plus half rho b2 square. But velocity becomes 0 at point 2, right? So this is equal to P atmospheric plus rho g h is equal to P1. But P1 should remain same. Let's suppose this is remain same even when that person is going to the mountain top, right? So when she is going to mountain top, P1 is equal to P, like let's suppose at the this will be at sea level, is equal to plus rho g 8.5 meter. Now when she moves to the mountain top, this is atmosphere mountain top plus rho g h. This is height climbed up the mountain. Now atmospheric pressure is decreasing but all total will remain same, so height will be increasing. That means height will be more as compared to like this is almost height will be at least double as compared to 8.5 meter. So obviously ABC 3 are correct only, but B is the most logical one, right? But if we take consideration into the point cavitation, so as we know, because of the forming of bubbles, when pressure inside the siphon tube reaches below the atmospheric pressure, we need to keep such a height that the pressure is above the atmospheric pressure. At sea level, the person can siphon up to a wall as high as 8.5 meter. But as she reaches the mountain top, the atmospheric pressure decreases to half of the pressure at the sea level. So the height, maximum height up to which the girl can siphon also reduces the half, because if it is more than that, cavitation will take place and we don't want that. So the atmospheric pressure of 58.5 kilopascal is insufficient to support 8.5 meter high siphon. So in that case, if cavitation is considered, then option C is correct, right? That is, height should be less than what it was in the sea level. Okay, let's proceed to the next question. A pitot static probe is used to measure the speed of an aircraft flying at 3000 meter. If the differential pressure reading is 3 kilopascal, determine the speed of the aircraft. Assume that the air flow over the aircraft is steady, incompressible, and irrotational with negligible frictional effects. Standard atmospheric condition exists and the wind effects are negligible. Take the density of the air at this altitude at as 0.909 kg per meter cube. So using the pitot tube, what do we need to find? We need to find speed of the aircraft. So simply for pitot tube, what we have already derived, the Bernoulli equation at point 1 and 2 will be applying here, right? So Bernoulli equation simply will be applying like if we are taking 2 points 1 and 2 between those 2 points, and with that we can get the pressure. So I'll give you 2 minutes to solve this, then we'll proceed with the solution. Okay, I think we should proceed with the solution now. So if this is the pitot tube that has been inserted into the flow stream, so here flow stream is there with velocity v. This is point 2 and this is point 1. This is stagnation pressure. Point 2 is the stagnation point. That means V2 is equal to 0 and Z1 is equal to Z2. Obviously, because it is in the same horizontal plane. Now, if we'll apply Bernoulli equation between point 1 and 2, P1 by rho plus V1 square by 2 plus Z1 is equal to P2 by rho plus V2 square by 2 plus Z2. This is stagnation pressure. This is 0 obviously because the fluid completely, like the air completely stops, right? This one cancels out. So P stagnation minus P1 is equal to 3 kilopascal. It's given already. It's shown in the pitot tube meter. The differential pressure reading, and density is given as 0.909. So V1 square by 2 is equal to P stagnation minus P1 upon density. So V1 is equal to root over 2 P stagnation minus P1 upon rho. So this is equal to root over 2 3000 upon 0.909. So this is equal to 81.24 meter per second. So this is equal to 292.48 kilometer per hour. So this is option D. Okay, so now this is the third question where a piezometer and a pitot tube are tapped together, like at 4 centimeter diameter horizontal water pipe, and height of the water columns are measured to be 20 centimeter in piezometer and 35 in pitot tube. Both measure the top surface of the pipe, determine the velocity at the center of the pipe. Very easy, like you already know the formula, you already know the basics of what is the physics has been applied, so you can clearly find it out. So I'll give you 2 minutes for this and then we'll proceed with the solution. I'll just come back. Okay. So let's proceed with the solution for this. Like if this is the pipe and this is the piezometer and this is the pitot tube. Mind my drawing, please. So don't mind that. Okay. So this is the head here and this is the head here. This is at a height of 35 centimeter and this is at a height of 20 centimeter. This is point 2 and this will be somewhat, just 1 second please. Let me make it a bit short. Yes. This is point 2 and this straight here, this is point 1. This is a steady flow, like this is 4 centimeter and this is a steady flow with straight and parallel streamlines, and thus the static pressure at any point is equal to the hydrostatic pressure at that point. So point 2 is stagnation point, thus V2 is equal to 0 and Z1 is equal to Z2. So now if we apply the Bernoulli's equation, P1 upon rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. So this will cancel out. This is 0. So V1 square upon 2g is equal to P2 minus P1 upon rho g. So R is the radius of the pipe. So P1 is equal to rho g height of piezo plus R. That is height plus the radius of the pipe. This passing through the center line. This is the radius, right? So radius of the pipe plus the height. So P2 is equal to rho g h of pitot height plus R. So V1 square, if you put in the main equation, 2g is equal to rho g h of pitot plus R minus rho g h of piezo plus R. So this is upon rho g. So V1 is equal to root over 2g h of pitot minus h of piezo. So this is root over 2g into 35 minus 20. So this is 9.81. This is 20 to the power minus 2 obviously to take it in meter, and this is equal to 1.72 meter per second. So this is option A, right? Now let's proceed to the next question. We have many more questions to go. So the water level of a tank on the building is 10 meter above the ground level. A hose leads to the tank bottom to the ground. The end of the hose has a nozzle which is pointed straight up. The maximum height to which the water could rise is which of the following? See, make sure you understand that at the end of the nozzle, like at point 2, the velocity, why this will be 0? Because here the inertia suddenly begins, like inertia becomes 0. That's why the fluid stop rising up, no, and it falls down. So inertia is 0 at this point. That means velocity is 0 at this point, right? So simply apply the Bernoulli's equation at point 1 and 2. I think you will just need 30 seconds most probably to solve this. Okay. Okay, then solve this. So should we, I think you have solved it already. So should we proceed with the solution then? Okay. So if we apply this is question number 4, right? So P1 upon rho G plus V1 square upon 2G plus Z1 is equal to P2 upon rho G plus V2 square upon 2G plus Z2. So V1 is equal to 0. Why? Because this is a huge tank. Again, the area is very large, so velocity is almost 0. So V2, sorry, P1 is equal to P atmospheric pressure and Z1 is equal to 10 meter. P2 is equal to P atmospheric pressure, V2 is equal to 0 and Z2 is equal to H. So that means Z1 is equal to Z2. That means H is equal to 10 meter. So if we consider frictional effect, so maximum height that the nozzle will be reaching, the nozzle jet will be reaching will be less than 10 meter obviously, because this is frictionless condition. So this is option C. Okay. Now a hollow cylinder of 0.3 meter is open at the top, contains some liquids and spins about its vertical axis, producing the force vortex motion. The situation with the liquid just begin to uncover the base, the height of the vessel so that the liquid just reaches the top of the vessel and begins to uncover the base at 50 rpm. Acceleration due to gravity is given. So this is a link question. So the questions are, sorry, no, just one second. Okay. So we need to, so sorry, this is we need to just find the height of the vessel. So the velocity at which the speed at which it is rotating is 50 rpm. So what we need to find? We need to find the height of the vessel at which the liquid rises, right? So I'll give you 2 minutes to solve this, and then we'll proceed with the solution. Like, let me give you an idea. Here, the flow is rotational, right? So, since the flow is rotational, this is a forced vortex. And here we cannot apply the Bernoulli equation in this region. So we need to apply the Euler equation that we have studied even solve the question in the previous week, right? So applying Euler's equation of motion in the r direction and the difference in pressure between the point 1 and 2, like if this is the thing, right, it is moving like this, right? So this is the axis of rotation, and we consider this as point 1 and this as point 2. This is height h. So the difference in pressure between points 1 and 2 can be found from, like, del P del R is equal to rho V theta square. We already know about this equation, right? We have studied it in the previous week. And here V theta is equal to omega R. So you can solve this now. I'll give you 2 minutes to solve this, and then we'll proceed with the solution. Okay, I think we should proceed with the solution now. So, as I've already said, we'll be using this equation because Bernoulli equation won't be applied here as it is a rotational flow. So, del P del R, so del P del R dr P1, if you integrate it, P2, we'll integrate it from 0 to R. R is the total radius, V theta square by R dr. So this is 0 to R omega square R square by R dr. So this is P2 minus P1 is equal to rho omega square R square by 2. So this is the radius of cylinder and angular velocity. So h is the height of the cylinder, and as the point 1 is at free surface, P1 is equal to P atmosphere, and point 2 is at depth h from the free surface. The hydrostatic pressure acts in excess to the atmospheric pressure there. So P2 is P atmosphere plus rho gh, right? So P2 minus P1 is equal to rho omega square R square by 2. So from there we'll get h as omega square R square by 2g. So omega is 2 pi into the RPM, that is 50 upon taking it to seconds square, multiplied by cos 0.15 whole square, 2 into 9.81. So if you will solve this up, this will be 0.0314 meter. This is option D. Okay, so let's proceed to the next question now. So air at 110 kilopascal and 50 degrees Celsius flows upward through a 6 centimeter diameter inclined duct and at a rate of 45 liter per second. The duct diameter is reduced to 4 centimeter. Obviously, this portion is 4 centimeter. The density of air and water are known to be 1.19 and 1000 respectively, kg per meter cube respectively. The pressure changes across the reducer measured by water manometer. The elevation difference between the 2 points on the pipe where 2 arms of the manometer is attached is 20 centimeter. Determine the differential height between the fluid levels of the 2 arms of manometer. Right? So it's very easy. Like we already know the formula, right? What do we need to do? So for manometer, like we simply need to apply the Bernoulli equation between the 2 points. So from there we'll get the height. Okay, I'll give you 1 minute to solve this because it's already late, so make it fast. Okay, so let us solve this up then. Like here, this is the duct. So here, 4 centimeter. This is 6 centimeter. And this is 45 liter per second. This is 0.045 meter cube per second, right? So this, we have just converted it. So this is the manometer, right? This is the manometer we have connected here. This is point 1, this is point 2. So distance between this point 1 and point 2 is 20 centimeter. So density of air is 1.19 and water is 1000. Now if we are applying the Bernoulli's equation between point 1 and 2, so we'll get from there P1 minus P2. I'm not going to much detail. You solve this up on yourself because it's already very late. So P1 minus P2 is equal to rho air V2 square minus V1 square upon 2 plus density of air G Z2 minus Z1. So V1 is equal to Q by pi D1 square by 4 is equal to 0.045 pi 0.06 square by 4 is equal to 15.92 meter per second. And similarly, V2 is equal to Q by pi D2 square by 4 is equal to 0.045 pi 0.04 square by 4. So this is 35.81 meter per second. So this is Z2 minus Z1 is equal to 0.2 meter. And from there, P1 minus P2 is equal to 1.19, 35.81 whole square minus 15.92 whole square upon 2. So this is plus 1.19 into 9.81 into 0.2. So this will give us 614.53 Pascal. The differential height of water in the manometer corresponding to this pressure change is determined from del P is equal to density of water GH. So H is equal to delta P by density of water G. 614.53 upon 9810. So that is 0.0626 meter. So that means 6.26 centimeters. So that is option. Now let us quickly proceed to the next question now. So similar to the previous question, there is a hollow cylinder and again we need to find the height of the vessel. Just values are different here. So obviously you can solve this up on yourself. So here we won't be going to the solving of this. So here you will get 0.503 meter, the height. But then similar, this question have a second part that is related to that. So in a physical situation, that is described in the previous problem, with the speed increased to 130 RPM, then what is the area of the base that is uncovered? So we need to solve this part because this part is a bit different. So I'll give you 1 minute to solve this and then we'll proceed with the solution. This is Okay, so what is happening if like when the speed is increased? When the speed is increased beyond 100 rpm, the maximum centrifugal head, that is omega square r square upon 2g, will be more than the maximum static pressure head, right? Rho gh, and hence the liquid being detached from the center and uncover the base. So if R1 is a radius where the free surface meets the base, if R1 we are considering as shown in the figure, the pressure difference between the points 1 and 2 will be P2 minus P1 rho omega square upon 2 R square minus R1 square. So also P2 minus P1 is equal to rho GH, right? So this will be equating, so rho omega square upon 2 R square minus R1 square is equal to rho GH. So R1 square is equal to R square minus 2GH upon omega square. So this is 0.3 square minus 2 into 9.81 into 0.503 upon 2 pi 130 by 60 whole square. So this is 0.037 meters square. The uncovered area of the base is pi r1 square is equal to 0.116 meters square. The minimum pressure during the flow is likely to occur at B. So obviously we can see that by applying Bernoulli equation, and hence it should be ensured that the pressure at point B is more than the atmospheric pressure too. So okay, sorry, I am just denoting the answer to the next question. Sorry, sorry, sorry. So this is the answer for this one. So okay. Mm, so this is which one option? Option B. Yes. So this is option B. As I've already said, in this question, there is nothing, right? So as we know that from point A to point B, like it will move from point A to point B, and point B, the pressure will be much lower than atmosphere. So in order to avoid cavitation, the pressure at point B should be higher than atmospheric pressure, right? So what is this called in the like what is said in the question? So it said that at which cavitation is most likely to occur. So it is obviously most likely to occur at point B. So answer is option C. For a liquid flowing through a closed duct, which of the following is true? A pitot tube can measure both stagnation pressure and static pressure. A pitot tube can measure stagnation pressure. A pitot tube measures the value of the volumetric flow rate. To measure the static pressure, the axis of the tube parallel to boundary duct. Obviously, the pitot tube can measure only stagnation pressure in case of flow through closed duct. Okay, so water flows through like with a volumetric flow rate is given through a 120 mm diameter orifice used in a 316 mm pipe. Find the difference in pressure head between upstream section and vena contracta section. So CV and CC are given already. So what we need to find? We need to find the pressure difference, right? So all the equations we already know, we have already derived in the class. So we just need to find the delta P upon rho G, the difference in pressure head. Okay, so I'll give you 2 minutes to solve this. I think it's very easy to solve this one, right? So let's wait for 1 minute and then we'll solve the solution. Okay, so I think we should proceed with the solution as it's already late, and we have many more questions to go now. So for question number 11, first the volumetric flow rate is, we already know that C is equal to, sorry, Q is equal to C delta P rho delta P upon rho G. So C here is CV CC A naught to C 1 minus CC square A naught square upon A1 square. So A naught upon A1 is given by 1/3. It's already given in the question, right? Okay. So diameter is given, so you can clearly find out A naught upon A1. So, and A naught is equal to pi by 4 120 square. So C is equal to 1 into 0.60 into pi by 4 into 0.12 square multiplied by 2 in 2 multiplied by 9.81, 1 minus zero point 0.6 square multiplied by 0.3333 to the power 4 whole square. So this is C will come out to be 0.03, and Q is equal to C root over delta P upon rho G. So this is 0.015, 0.03 root over delta P by rho G. Therefore, delta P by rho G is equal to 0.25 meter. That is option. Okay, so let us proceed to the next question now. It said that the flow section of a laboratory wind tunnel is given. The total head pointed upstream indicates the stagnation pressure, and the test section center line is stagnation pressure is given as 10 mm of water below atmospheric, below atmospheric pressure. The laboratory is maintained at atmospheric pressure and temperature of this. Determine the static pressure of the wind tunnel's test section. So it's very easy. The stagnation pressure is equal to atmospheric pressure minus rho gh, right? So atmospheric pressure is already, we know, 101,325 Pascal. So rho gh is given as 0.01 meter, right? 10 mm is given, no? So from there we'll get the stagnation pressure. And also we know that static pressure is equal to stagnation pressure minus dynamic head. So static pressure, sorry, stagnation pressure is equal to static pressure plus dynamic head. So static pressure will be stagnation pressure minus dynamic head. So simply we can calculate this. So let's calculate this. So stagnation pressure P is equal to, this is question number 12, P atmospheric pressure minus rho GH. So this is 101,325 minus 1000 into 9.81 into 0.01 is equal to 101,226.9 Pascal. Now this is stagnation pressure, right? Now dynamic pressure will be is equal to half rho v square. So 0.5 into 1000 into 50 square is equal to 125 chatta 0 40 Pascal. So the static pressure will be is equal to stagnation pressure minus dynamic pressure. So 101,226.9 minus 12540. So this will be minus 1148773.1 Pascal. That means option D. Okay. So let's proceed to the next question now. In a certain application, a siphon must go over a high wall. Can water oil with a specific gravity of 0.8 go over a high wall? Obviously, the siphon can be used over a higher wall as long as the free surface where the siphon is discharging is below the free surface of the liquid. And also the height of the water wall should not be high enough that the pressure of the liquid becomes less than the atmospheric pressure at a given temperature in order to avoid cavitation, obviously. So this will be option A. Next question. So how many questions are left? We have got 3 more questions. So in this question, there are three parts, right? So two identical orifices are mounted on one side of the vertical tank as shown in the figure. The height of the water above the upper orifice is 3 meters, and the jets of water from the two orifices intersect at a horizontal distance of 8 meters. So CV is given 1 as for the orifices. So what is the velocity of the discharge of water from upper orifice? And the vertical distance of the point of intersection of the jets from the water level in the tank, and what is the vertical distance between the two orifices. So it's very easy, like you have already solved this kind of question, so I'll give you 2 minutes to solve this and then we'll proceed with the solution. Okay. So how to approach this question? First of all, let's suppose u1 be the velocity of discharge from the upper orifice to and T be the time taken for the water to reach the point P from the upper orifice. Like if I go to this question, this is the upper orifice, right? So this is the upper orifice. So let U1 be the velocity of the discharge from the upper orifice to the point P, to this point. So H minus 3 will be equal to half GT square. So, and also U1T is equal to 8, right? So, if we will equate this, H minus 3 is equal to 32G upon U1 square. Now, applying Bernoulli's equation between the top water level and the, like, between this point, like if, let's suppose, uh, this is point 1 and this is point 2 for now. So, if these are point 1 and 2, then by applying Bernoulli equation between these 2 points, we will get u1 square is equal to 6g. So, u1 is equal to root 6g. That means option, which one? Option B, right? So, this one is the option for the first question. For the second one, again, what is said, the vertical distance from the point of intersection of the jet in the water level, like we need to find out this h. So this is h minus 3, we have found out that 32g u1 square, so u1 is equal to root over 6g. So if we will equate in this main equation, if we will replace there, so h will, like the value of u1, so we will get h is equal to 8.33 meter. So that is option A, right? What is the vertical distance between the two orifices? So for that, we need to first find out the U2, right? We need to first find out the capital H we already know. We need to find out the small h. So then this will give the vertical distance. So if U2 is the velocity of discharge from the lower orifice, so H minus 3 minus small h is equal to half GT square. So, and also U2T is equal to 8. So, H is equal to 8.33 meter. So, applying the Bernoulli's equation between the top water level and the lower orifice, that means at this point, the point 2 will be this one, right? That means point 2 will be this one. Okay. So, if we will apply this, so again, U2 square is equal to 2G H plus 3. So, H is equal to 2.33 meter. So, this is the distance between that. 2.33 meter, that means option C. Next question, which of the following statement regarding the venturimeters is not true? Obviously, while flowing through the converging part, the pressure difference according to the Bernoulli's theorem and velocity increases. That means option D. Okay. Last question for today. Water is flowing through the venturimeter whose diameter is 7 centimeter at the entrance part and 4 centimeter at the throat. The pressure is measured to be 380 kilopascal at the entrance and 200 kilopascal at the throat. Neglecting frictional effects determine the flow rate of the water. Okay, so this is very easy. Again, apply the Bernoulli's equation and then find out the velocity. From that, the volumetric flow rate. I'll give you 1 minute to solve this. This is very easy. Okay, so let's solve this last question. So first of all, if you'll apply the Bernoulli's theorem between the entrance and the throat, so P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 is equal to GZ2. So A1 V1 is equal to A2 V2, V2 is equal to 49 by 16 V1, Z1 is equal to Z2. So putting the values in the first equation, so this will be 380 plus V1 square by 2 is equal to 200 plus 49 square by 16 square V1 square by 2. So V1 is equal to 6.554 meter per second. So volumetric fluid will be pi by 4 d1 square v1, and this will be equal to 0.0252 meter per second. So that means option A. Yes, so that's all for today. So I hope you enjoyed today's session, and I'll meet you all next week, same time. Okay, bye, good night.